Hello, everyone. Okay. So today, when I'm starting, I just want to start with something that happened in 2019. A group of scientists, researchers who had spent years, probably the whole career, working on one single problem, sat in front of their screens and cried that day. Not because something went wrong or like something, but it went right finally, and they had just seen black hole for the very first time. Now, I want you to think about what that means for 1 second. Black hole is a region of space where gravity is so extreme that nothing, not matter, not gas, not even light, can escape once it crosses a certain boundary. Which means, by definition, you cannot photograph it looking by just directly at it because there's no light coming out of it. So, how do you photograph something that cannot be seen? You photograph everything around it, the superheated gas, the plasma spiraling around it that is glowing, and the black hole, it's that glow. And that shadow, that dark circle surrounded by a ring of fire, is something that you see in this image. And it took 8 telescopes on 4 continents and more than 100 years after the mathematics first predicted it that black holes should exist. That is the reason that scientists cried that day. So they're not surprised that it was real. They were surprised, they were happy because they waited for the entire lifetime to get it confirmed. So I just want to know, did you really think that a black hole could be photographed? Mhm. Okay. So yeah, the people who said yes, they are correct. But the people who said no are also correct because until 6 years ago, the correct scientific answer was no, we cannot do this. We don't have that technology. And then we finally did. And that is the version of science I want to talk to you today. Not the version that we see in the textbook, where everything is settled and clean and the answers are available in the last page of that book or that chapter. The version today that we're going to see is where things are genuinely unknown, okay, and where discoveries happen in real time with us, and where the most powerful sentence may be, I don't know about it yet. That yet is very powerful over here. So let's start. So I'm Smriti, and I'm a computational astrophysicist. That is just a complex way of saying that I write code that might simulate something like the sun, the stars, their magnetic field. So my instruments are not telescopes. My instrument is Python scripts, mathematical models that may fail many times before they give me something that is actually true. And I work at Lab of Future. And for the next 30 odd minutes, just bear with me because I want to show you that leaving version of space science or astronomy, how does it look like? We'll cover three things today. What we astonishing that even though we know about it or we realize about it, it's too late. And then what we genuinely don't know. And the scale of unknown is humbling, and how science actually works, because that part is the most misunderstood of all. So let's start with what is known, because even the things we have confirmed are genuinely very strange. So in 1992, we had confirmed exactly zero planets outside our solar system. Not a small number, zero. We had strong theoretical reasons to think why they should exist. We had mathematical models suggesting that they were probably everywhere, but there's no evidence to it. Today, we have confirmed around 5,700 of it. And I want to tell you about one system in particular, that is the TRAPPIST 1. Because how we found these planets and why the discovery matters so much to humanity. It's called TRAPPIST 1. It's a small, cool, dim star, much, much smaller than our sun, sitting about 39 light years away. That sounds far. On a cosmic scale, so TRAPPIST 1 has 7 planets. All of them are nearly roughly Earth sized. And 3 of them fit in what we call the habitable zone, the range of distance from a star where liquid water could exist on a surface. So, not guaranteed, but it's a possible reason. Am I audible to everyone? Yeah, great. Okay, so okay, TRAPPIST 1. So yeah, there, there we were. So the 7 planets, they are at a range of distance from a star where liquid water could exist on every surface, possibly. It's not guaranteed, but it's possible. So those 3 worlds could have oceans and they could have a weather just like Earth, and they could, in principle, have life. Now, here's what I find genuinely interesting to say out loud, because we did not find these planets by just seeing them. A planet orbiting another star is far too small and too dim to observe directly. The star's own light can overwhelm it. Just like how you are flashing a torchlight on someone, you might not be able to see, overwhelm it completely. So that what we did instead, we watched the star, not the planet. So when a planet is passing in front of the star, from our point of view, it is blocking a tiny fraction of that starlight. That is just like how a solar eclipse or a lunar eclipse happens. We just found that the brightness has reduced. There's a dim or a dip in the brightness that is happening. The star gets very slightly dimmer, and we are talking a fraction of a percent for a, then it brightens again, just like how the eclipses do. So now we plot that brightness over time and we get a shape called a light curve. You can see over here the few light curves that we have seen. Okay, so this brightness over time will get us these light curves, and the depth of these dip tells us the size of the planet. So the time between the dip tells you the orbital period, and the orbital period tell you the distance from the star. So when we are, just because a light, just because or the dim or the dip of that brightness, we could find out a new system, a new system just like a solar system. So this technique is called transit photometry. And I want to mention, because this is what probably I have worked on so many times, because this exact same method I have used to model binary stars. 2 stars orbiting each other, they take turns blocking each other. The physics is almost identical. So from the stars to planets to anything, a same phenomenon can be used. The tool is identical, but at totally different scales. So the scales from 2 stars to a planet and its star. So when I first made this connection in my own work, it was one of those moments where you feel like, oh, how deeply unified is the underlying physics of all of that. We know that there are exoplanets there, that we know that there are many more planets over there, and this is one of the system that we know about. And black hole, let's come back to it. We just talked about it, about the photograph in the intro, but I want you to give a bit more physics to it, because the image is itself very strong than it appears. When you're seeing that photograph, it's not that black hole itself, you can't see that. What you're seeing over here is the accretion disk, a superheated gas and dust spiraling inward, reaching temperatures of billions of degrees, and it's glowing intensely. Now, the dark circle at the center is the shadow, the region where the black hole's gravity is bending and swallowing all the light that would otherwise just reach us. So, the black hole in that image is M87, and it sits at the right at the galaxy called Messier 87, about 55 million light. trillion billion times of the sun. And if we are replacing sun with M87, its event horizon, the point of no return, would extend far beyond the orbit of the Pluto itself. So, and here's one thing that still gets me. Einstein's equation predicted this in 1915, not approximately, with enough precision that when we finally photographed it in 2019, the image matched the exact mathematical prediction almost exactly. 104 years between the theory and the proof. Science works like on long time scales. I'm pretty sure people are having some doubts and they want to ask few things. I would request you to put that in the chat box over there. We have finished this webinar. So, and next thing that I would want to talk to you about is gravitational waves. That I think is more profound conceptual shift in all of modern astronomy. In 1916, again, Einstein predicted ripples in space-time from a massive accelerating objects. He thought that it would be too small to ever detect because they don't just get affected by gravity, nearby matter through gravity. So they send ripples through the fabric of space-time outward in all the direction at the speed of they are spread over there when you drop something into the water, but except the water is the geometry of space, not anything else. So Einstein predicted these ripples and then he calculated how large they would be by the time they would reach Earth from any realistic source. His answer, impossibly small, smaller than any instrument we could build would ever detect. And he thought that this was a prediction that would never be confirmed ever. But in September 2015, we developed an instrument called LIGO, which detected than a second. It was a distortion of a space smaller than 1,000th of the width of a proton. And it came from two black holes, each roughly 30 solar masses, and they're spiraling together, merging in a collision that happened over a billion years ago. That is more than billion light years away. Now, it also has a deeper meaning. For all human history, every civilization, every astronomer, every telescope ever built, everything we know about the cosmos came from one thing: light. We had one sense in 2015, we gained a second sense. We can now, in the universe, not just look at it, we can feel the ripples. These gravitational waves pass through matter completely undisturbed. They carry information about events that no light could ever reach us from. And we have opened an entirely new window out of it. Now, can you guys please let me know which one of these three surprised you the most? Exoplanets, the black hole, or the gravity waves? Can you please let me know about it? Okay, I can see some are saying exoplanets, some are saying black holes, but most people are saying gravitational waves. I was wrong. I thought people would say black hole. Okay. So right now what we covered was three of the most remarkable discoveries in modern science. Thousands of new worlds, a photograph, a century in the making, a second sense for the cosmos. And you might be thinking, we have actually figured out quite a lot. We are doing well. That feeling, I want you to sit with that for 1 second because it is about to get complicated because everything I just described, all of it concerns just 5% of the universe that we know about. Because all of it that I talked about concerns matter and energy that interacts with light in some way. So when I'm adding all of that up, every star, every galaxy, every planet, whole, even every atom in the observable universe, we get only 5%. The other 95% is something else entirely, and we have no idea what it's it. That 95% of the unknown universe is still to be discovered. It's not poorly understood, it's not partially mapped, it is completely unknown. We know what it is doing. It's if I'm seeing that there is 95% unknown, that means it must be doing something, right? It is doing something. The gravitational effect, the expansion behavior. We always say that universe is expanding, but we cannot see it. We cannot detect it directly, and we do not have a working theory that explains what it actually is. So that is dark matter. Like about 27% of the universe appears to be what we call dark matter. And here is how we know it exists. When you look at a spiral galaxy, have you seen a galaxy rotating? All the stars and the gas and the clouds orbiting around the galactic center. And you measure how fast the outer edges are. And something is wrong over there. Because as we know, from in our solar system also, the planets which are further apart from our sun are a bit slower than how faster the Mercury or Earth is. Okay, but here the galaxy's edges are moving faster. In a normal gravitational system, the things further from the center should orbit more slowly. The way and but galaxy rotations are flat, the outer edges move almost as if it is like moving the inner parts of it. So the only explanation that works over here is that there is a massive halo of invisible matter near extra gravitational pull to it. And that unknown thing is we call it a dark matter. We have mapped where it would be, but we do not know how it would be. We know how much time it there must be. We have no idea what it is made up of though. It does not emit light, it is not absorbing any light or interacting electromagnetically in any way we have detected. It is just pulling. That pulling force of gravity is the only thing we know of. And the only explanation that works here is that the massive halo of invisible matter surrounding every galaxy is the extra gravitational pull. Now, that is dark matter. And we also have dark energy. Now, dark energy, which is more strange because that universe total energy content. So what we have understood from the existence of something of the universe is accelerating. So after the Big Bang, the universe is expanding rapidly. Now gravity should be slowing it down, but that expansion is not slowing down. Then in 1998, two independent teams started measuring distant supernova that are found in the galaxies. Supernovas are the form a part of the star's life cycle where they are burst almost done by their life cycle and they start bursting and they are releasing energy out. So we started measuring those two supernovas and found that galaxies are not just moving apart, they are moving faster and faster. That means something is pushing space itself out, that overwhelming gravity on the largest scale. Now we call that something as dark energy. And we have no physical description of what it is, or the best we can say is that empty space appears to have an intrinsic driving to its acceleration. And I know that is not a satisfying answer because I myself am not satisfied of it, but it is the honest one till now. Now, the next thing is something that I myself has worked on myself, but I also did not get any answer. But here it is, the solar corona. Uh, I want to bring this like because you know sun is very long. We know it is so where it is, but it's an open question. It is the center of our life system, our own solar system. The surface of the sun is 5,778 Kelvin. is the temperature. It is hot, extremely hot. But as you move upward from the surface, in the outer atmosphere of the sun, the region is called corona. The corona is the region that you can see over here on apart from the disk here, which is the atmosphere of the sun, which is plumed by flares, there are ejections happening, there are jets happening. And this region, corona, here the temperature is increasing dramatically. The corona reaches temperatures of 3 million Kelvin. Now, the surface we saw in Kelvin and the atmosphere is at 3 million Kelvin. It is hard to register, but the as far as we go from the sun heat source, it is getting hotter, which is something that no one has understood till. It is violating every laws. That is the second law of thermodynamics. Heat is flowing from hot to cold, not the other way around. And you do not get warmer stepping away from a fire. That because normally when you're near the fire, that is where the warmth is. When you're away from it, you don't feel the warmth, but here it is completely opposite. And yet the sun's corona does exactly the same thing. And we have been aware of this problem since 1940s. We have decades of observation, satellite data, and we still do not have a confirmed mechanism of why this is happening. We have a lot of hypotheses. The two leading theories are magnetic reconnection, where the sun's tangled magnetic field snap and reconnect, and it releases energy directly to the corona. That is the Alphen wave dissipation, where oscillations travel through sun's magnetic plasma and not directly the energy into the coronal plasma as they travel upward to it. So now both of these cases of Alphen waves and the magnetic reconnection, both of them are plausible. But right, but that ambiguity is still the frontier of the whole problem of corona. So what I did for this, as I wrote MHD models, which treats the sun's plasma as a conducting fluid. It governed the whole fluid dynamics, the electrodynamic equation simultaneously, and I got some jets that are coming out of it. I predicted the whole model, but still the answer was not yet confirmed to it. And I did show that model here. This is the actual satellite data that we have got, and these blue green stuff is what the modeled stuff that I did. So this is how the solar corona problem is also there. So I want you to tell me, in a scale of 1 to 5, how comfortable are you sitting, 1 being very uncomfortable and 5 being completely fine? I mean, I'll find it later. What is your take on this? Can you all put that in the chat box or the poll? Okay, I'm waiting for the answers. Okay, so you're comfort. Most people are comfortable sitting with it. Some people are not, and that I am not so comfortable sitting with an answer. I don't know. I would probably work on it, and most of us work on it, and that is what science need. This is okay. We have gone through what we know of. We have gone through what we don't know about it, but there is still one big open question to all. That is, are we the only life in the universe? We genuinely do not know. And that is the most exciting sentence in the science. because we genuinely do not know if it is actually correct, or we do not know if we are actually very alone in the whole more every day. We have also explored only a vanishingly small fraction of the universe, which contains approximately 2 trillion galaxies, each containing hundreds of billions of stars, most of which appears to host planets. Uh, the James Webb Space Telescope is actively working on this. Distant star passes through the atmosphere of its planets, different molecules absorb different wavelength of light, leaving chemical fingerprints in the spectrum. Oxygen, methane, water vapor, ozone, all of these are the biosignatures, the exact thing that we might be looking out for when we want to know if there is life there. And the only process we know of that is to check for these biosignature. We have not found a confirmed biosignature yet. So we have the strange picture right now. We have confirmed things that seem by questions we cannot answer. That is the 95% of the whole universe, the sun breaking thermodynamics, life being unknown. And then you might be asking, how do scientists live in that? How do we keep working on something we don't know about it yet? And will we ever solve it? These questions are the ones that make how science actually works, what the process really look like from the inside. This is what we need. I'm pretty sure you guys are having lots of questions right now, and I would like to answer them. Uh, we could just answer 2 or 3 questions first, and then we would go back to how science is actually doing things. Does that work? Okay. I can see few questions over here. Okay. Let's see what we can. Let me see some questions. Reaches the end of the universe. Okay. Okay, we possibly imagine Big Bang as an explosion into empty space, but normally space itself expanded every. There is no confirmed outer shell to the expanding emptiness. So the universe is infinite. There is no starting point or there is no ending point over there. So I guess that answers this question. And then we are having, could singularities be the entrances to wormholes? Okay. Uh, in mathematics, possibly, but in physical reality, no, because at least that is what the current evidences have told us. So, what your question is, it's touching the real idea in the general relativity. Some solutions of Einstein equation mathematically gives this answer, but in physical reality, we have not reached yet over there. So yes, taking about singularity in general relativity, singularity is not just literally a tiny physical object. It's place where our equations finite, but we have not found that at all. So that already creates a conceptual problem. The theory breaks predictions about wormholes emerging from it completely. So yeah. Do we have any other questions? Okay, my child was asking what is a white hole. Yeah, that's a very good question. We have talked about black holes, but we did not talk about white hole. So black holes are in a black hole, things enter and nothing can escape. But in a white hole, things can escape and nothing can enter. So mathematically, relativity allows such solutions. Physically, where the idea comes directly from reversing the equation of the whole black hole mathematically. So, in short, to a child, I would say it's just the opposite of a black hole, because in black holes, things are entering, and in white hole, things are escaping out and they cannot enter back again. Okay. So now let's see how science is actually working. Uh, Normally, your textbook says a lot of answers already to you, and we memorize them, we reproduce them in an exam, and we move on. But we never ponder on that particular topic. That is the archive of science. The things that have already been settled enough, write them down, and that is all. That's where the whole curiosity stops. But science is a process of being wrong in productive ways. So before 1924, we thought Milky Way was everything, but no, we are finding more galaxies altogether. In solar physics, also, we are modeling wrong things repeatedly, and then we correct them later. Everything that issues there have had some problems. If we stop finding those problems, we stop doing science. So I don't know is one thing that I said initially, and I want to that again, because I don't know in a single honesty and rigor. Is someone is saying that uh, if I'm having all the answers and I'm telling you that, maybe it is something that you want to hear. But someone who says I don't know here is meaning that I am doing that to find out what is it. Just like how Event Horizon telescope collaboration had over 200 researchers across 20 countries. They spent years on a problem where failure was most likely an outcome. They built it anyway. And when the image appeared on their screens, matching Einstein's predicted black hole exactly, and that's the moment scientists cried, because 100 years of people being wrong in productive ways had finally accumulated into something that is true. So science is, it moves through uncertainty, it updates when it is wrong, and it takes longer than anyone wants it to be. And this raises a practical question, particularly about what their children should study or build. If the frontier of knowledge is this far out, if the open questions are this large, what does engaging with this? Not in 20 years when you might have a PhD, but now in school, as a student, as a 10-year-old, what is something that I want to show you? So science is always broken. That is how it's usually taught. So then I want to show you what fixing it would actually look like. Most student I encounter the universe, teacher is drawing something on the board, we copy it down in our notebook, and you memorize it for an exam, and then nothing. The law remains a stranger. It lives in your notebook, but not inside you. The problem is not the law. Problem is not Newton. Problem is not Einstein. Problem is not Kepler. The problem is the history of human thought. The problem is that we were told about it, but instead of made to discover them, there's a profound difference between these two things. So at Lab of Future, we build not just a course, not a workshop, not a set of activities that you should be doing, but we're building an ecosystem. And system I want to use deliberately, because an ecosystem is not a collection of separate things. It is a set of things that would feed into each other, that would need each other, that would make sense together. Curriculum is the foundation. Is very not the ceiling, it's not the end of it. The physics your child is already studying in the school, the mathematics, the science, that is the soil. And what we should be doing is planting something in that that grows up into research, into real instrumentation, into problems that don't have an answer yet at the back of the chapter. It should in front themselves, and the growth is also the same, from passive to active. We don't want passive learners who just read some. We want practice. Your textbook is stating Kepler's law, but how do you know how? Telescope, have you ever looked from one? Have you ever made one? spectroscopy, about rovers that we are just seeing, would know how to navigate through obstacles, the problem solving when it doesn't go and here is what I really want the parents if they have joined today, because this is the part that gets lost in conversation education. When a student is building something that fails and then they figure it out why, they are building resilience over there. When they look at a problem that has no solution printed in the book that they are having in their hand, they have a reason to look forward for an answer. They are building their research instinct. And when they have everything to explain why the telescope isn't finding the star like it should be, they are building the ability to communicate complex ideas clearly. When they iterate, adjust, and try again, they are building the tolerance for uncertainty that every scientific career demands, not just. These are not soft skills. These are the skills that will define someone can work on any frontier of any field, not just astrophysics, the jobs that will matter in 10 or 20 years, which might not even exist right now. Or qualification for those jobs is not knowing a fixed body of how to work on an incomplete information. So this is for people who are persistent. This is for people who wants to collaborate into major discoveries. They want to be honest. So now when I say on something that I don't know, will you trust them more that okay, I can build on something, or will you be like, okay, textbook? So before we end the Q&A, I want to bring back that this field is not a collection of settled answer. It is an ongoing reality conducted with mathematics, instruments, simulations, physical experiment, and occasionally with a lot of patience. And every open question that I described today, dark energy, dark matter, corona, the question of life, the problems left over from the scientists that who aren't smart enough to solve them. They are the frontier. The people who will solve them are younger than anyone currently working on them, might be in this call right now. So I don't know if it's not a failure, it's a complete answer. And it is from where the next question would come from. So I would like to start with some Q&A right now. Let's see what are the questions that we are having. Can you just drop down your questions, Rayo? Okay. Um, I guess people can unmute and ask now, or I'll just take from here directly. What were these questions? Okay. Are gravitational waves the fifth dimension? If so, why and what are they? No, gravitational waves are not the fifth dimension. They are ripples in space-time caused by massive objects like black holes or so some it's a common misconception that something invisible is moving through space must be another dimension, but no, it is not in another dimension. It is just in the same dimension as we are living in right now. So then we have another question, which is what would a person falling into a black hole look like to an observer externally? Okay, to an external observer, the person would appear to fall slower and slower as they're approaching the event horizon. That is the faint. It might look like they are frozen in space time all over. And then we are having What questions? How can we detect exoplanets? So yeah, there would be something or else that is happening in the light curve formation, the size of the light curve, the orbital period of the light curve, that would tell us this a planet over there. Uh, okay, what causes dark matter is another question that I can see over here. We do not know, like, matter, because what we know is that something invisible is producing extra gravity in the universe. That is what dark matter for us is now, because evidence that we are getting is gravitational curves, lensing. There are many galaxy cluster dynamics that are happening, that is a whole cluster of galaxies together, and the cosmic microwave background are there. We are having question next is, what is graviton? Okay, gravitons are hypothetical quantum particles that would carry some gravitational force similar to how photons carry normal electromagnetism. So it is just like photon, but for quantum mechanics is what I would say. Is there a possibility that there are more planets like Earth on which humans could live? Actually, I don't know, but there is possibility, because there are many exoplanets which we could not find a biosignature yet have life, because for complete biosignature analysis we need to do few things more. So yeah, we have to know a lot many more things to know that, yeah, are there planets like Earth actually available? We have found few planets, but to actually confirm a life over there, we have not done yet. Then we have uh, Big Bang, Big Crunch, and Big Bounce. These are all hypothetical stuff that we don't know about yet. So, yes, there are things that we do not know. Big Bang is one of the most profound hypotheses that we know of how universe started. And yes, then there are Big Rip and the heat death of the universe. All of them are there, but we do not know how the universe will end for sure. Not answer to you right now. Uh, can wormholes be the start and end of the universe? No, uh, it cannot be. So yeah, these are, so those were very interesting questions, and I would like to answer more of them, but we are running out of time, and I would like to connect with all of you and all of your answers again. And for that, I guess Shrishti could help us, and she would tell you how to join with us more, and how can you get more of your answers clarified with us. So, Shrishti, over to you. Can you please tell them how to get back with more of their questions?
Yes. So thank you everyone. Thank you for joining for today's session. And big thanks to you, Smriti, for leading such an very exciting sessions and helping us to explore about this universe. So, guys, I hope you guys have enjoyed any. I know you have a lot of questions for us, but then we are running out of time. So, before that, for all your questions, we have answers. Let me just share you. So, before we close, we want you to welcome to the Lab of Future. It's a community called Curiosity Crew, a space where young explorers like you can join a lot more events and complete more fun and very much big activities, like maybe what quizzes, not just quizzes. We have master class coming up. We have a lot of other webinars coming up. So today's session, it's just the beginning of your bigger space journey. It's not just one right now, but it's like beginning your a learning journey with our lab of future. So, because you have joined today's session, you already earned 50 space credits. Think of space credit like your learning points inside Lab of Future. The more you participate in the activities, quizzes, events, and missions, the more credits you collect. And today you joined us officially, your journey has started with us. To keep growing your credits, complete more activities, learning missions of Lab of Future. Every quiz, every mission helps you move forward. Here is what exciting part. Once you reach 100 credit force, you can unlock a special discount for our upcoming masterclass, where you will learn more on Mission Cosmos. It is just a session 1 launch of mechanics, which will be taken by Smriti. Of course. So, at the continue directly, our upcoming session take a deeper into planets, rockets, space missions, astronomy, a real world science. Today, give you we just gave you a glimpse of masterclass where you can know deeper and level up your young space explorers. To continue from here, you can scan the code and download Lab of Future app. Inside the app, you can have the access of upcoming webinars, masterclass, quizzes, learning activities, community updates, and space credit opportunities. Also, please, everyone, please scan the code. I believe everyone can see the code.
No, it's not visible.
That is not visible. Okay. Now, can you guys see the see now the score?
Yeah, it's visible.
Okay.
I guess I'm still sharing my screen.
Yes, 1 second. Is it visible now?
People want to see it again, I guess. Can you show it again?
Yeah, yeah, showing it again. Is it visible?
Can you do full screen, Shrishti?
Yes. Okay. Now is it visible, guys? Is it visible, Smriti?
Yeah.
Okay. And guys, to you, I know you guys want a certificate. We have a certificate also. So please send your full name to community@laboffuture.com. So where you will be getting your certificate for today's session. Okay.
Thank you everyone who joined us for the session today. I am pretty sure I'm getting still get see few messages that they want some answers. Please join us with the Curiosity crew and you'll get all your answers there.
You can
Okay.
ask your questions even in the mail as well.
Yeah, you can also ask any of your questions in the mail as well. A lot of your answers would be clarified in the masterclass too. So yeah, please join the masterclass as well.
Okay, thank you once again for joining us for the and special thanks to Smriti for a wonderful session. Keep
Welcome.
learning, keep exploring, and please keep be curious. See you in the next
Okay.
mission, guys.
Bye guys.
Bye, guys.